In this lecture, I am going to talk about gradient of a function and normal to a surface. The main goal is to illustrate how a gradient f is normal to a surface. We know that f of x, y, z, any function of three independent variables equal to a constant. So this is a level surface for a given value of c. F x y z corresponds to a set of numbers that construct a surface. Okay, so maybe a simple example would be z equal to x square plus y square. So we know that z equal to x square plus y square is a paraboloid. We can rewrite that as f of x, y, z equal to x square plus y square minus z, which equal to 0. So I have c equal to 0. So f of x, y, z equal to c, which is a level surface. Okay. So if I have the paraboloid, so we should definitely look like that. Suppose that I have a curve on the paraboloid. Which is on the paraboloid does not matter which way it goes. And this curve can be parameterized by r of t. Okay, so if I have a curve that is parameterized by r of t, I can generally express that as x of t, y of t, z of t. So then my function f is a function of x, y, z, but x is a function of t, y is a function of t, z is a function of t. So we can utilize some idea from multivariable calculus about the total derivative. So total derivative, say now f becomes a function of a single variable t. F is a function of multiple variable x, y, and z. If I differentiate f intentionally with respect to t, so f is a constant, so it's dc dt equal to 0. Okay. So now df dt, which is the derivative of f with respect to t, but since f is a function of x, y, z, we can use a partial derivative of f with respect to x, use the chain rule dx dt plus df dy dy dt plus partial f partial z, or I would say df dz dz dt, and this equal to 0. So this is nothing but the well known that we know the partial derivative and total derivative. Okay, now by looking at this we can see that this can be expressed as a dot product, which is partial f partial x comma partial f partial y comma partial f partial z dot dx dt. I can use the shorthand x prime y prime t z prime t equals 0. So this you can write as a gradient of f dot r prime t shorthand. But now for any curve, parametric curve r of t, r prime t is a tangent. So if the curve lives on a surface, then the tangent also will be a tangent to the surface. Okay. Gradient of f dot r prime t equal to 0 means gradient of f is normal to r prime t. Gradient of f is perpendicular or normal to r prime t. R prime t is a tangent to the surface, corresponding surface defined by the function. So we can see that in very simple mathematical construction, differentiation tells us that if I have a function f, then its gradient will be normal to the surface. So gradient denotes the normal direction. So if you take any function, for example, just consider a plane for which we do not need a gradient to understand the normal. So for this plane, we have already learned that this plane has a normal direction 2, 3, -5. So normal direction is 2, 3, -5. Okay. Now we take this function as this plane as a function. So you write down this as f, and 2x plus 3y minus 5z. You can set this equal to 9, or you can set minus 9 equal to 0. Doesn't matter. It should be the same thing eventually. So now you take the gradient of f. So partial f, partial x is 2, partial f, partial y is 3, partial f, partial z is -5. Okay, so we can see that this equal to the normal from our known definition of normal of a plane. Just a quick reminder: the equation of a plane. So if I have to write the equation of a plane, it will be ax plus by plus cz equal to t. Okay, and from that the normal is generally, say, you can denote the normal by n hat, a comma b comma c. Okay, so hopefully this is now clear that if anytime we want to calculate normal to a surface, and if we know the expression f for the surface, we can take the gradient regardless of the function is a plane or a paraboloid or a sphere, any surface represented by a function. The gradient will be the direction normal out of the surface. Thank you.